And I see in the background you've got the Saturn V model, which I've also got at home.
Yes.
Not quite a place. Mine's rather dusty now, but I see good to see one of those after 50 odd years. But if I may, Colin, thanks very much indeed for standing in and for letting Sandra do this afternoon. But if I can pass you over, passed over to you to take it forward. Thanks very much indeed.
Okay, no problem. Let me just try and share the presentation. And now, do you see the right version of it, or the full screen version?
We see latest news in spacecraft explanation of comets and asteroids.
Okay, yes, checking, because sometimes it shows the wrong screen. So.
No.
Okay, well, thanks very much for the invitation to come and give the talk. It's yes, a pity we aren't all up and enjoying being on space sides to do this, but yes, as I said, hopefully next year. So I'm going to tell you a little bit about some of the missions that we have in the solar system at the moment, looking at comets and asteroids, and some of the ones we're working on for the future. One of the nice things about working in sort of solar system astronomy is that you have the ability not just to observe these things with telescopes, but also to occasionally go out there and poke things with sticks. And I'm particularly interested in comets, but also work in asteroids. And as we'll get on to, the distinction between these is becoming increasingly blurred these days. So I thought I'd start by giving a little tour of what's going on in the solar system at the moment. There's these very nice maps, which you can see here on the right, that will be, I'll zoom in on in a moment, so you can see in a bit more detail. These are produced by the Planetary Society, and so they update these every few months, and it gives you a map of where things are in the solar system at the moment and where various missions are relative to various planets and things. And what you'll see from these is there's quite a lot of missions at Mars, either on the surface roving around or in orbit around. There's a whole bunch of things in the inner solar system studying the sun and the heliosphere and the interaction between the sun and the planets. We have the Juno mission at Jupiter at the moment, which I'm not going to talk about, but if you haven't seen the movies of Jupiter from it, I encourage you to go and spend a lot of time enjoying those, because they are really spectacular. The Voyagers are still operating out now getting into interstellar space, and of course there's New Horizons, which is not that far away yet, but also speeding away through Hubble. I said I'd zoom in a bit on some of these on this nice map. So the outer solar system, you can see there's not so many missions out in the very outer solar system at the moment that are active. Of course, we had Cassini at Saturn for many years, but that ended a few years ago now. Juno is at Jupiter. In a few years' time, the European Space Agency will launch JUICE to go to Jupiter, which is will explore the moons of Jupiter. And then, yes, you have New Horizons in the outer solar system, and Voyagers still going strong and leaving the system entirely. If we zoom into the inner solar system, you can see that there's a few more missions around here because it's a bit easier to get to. As I said, there's a whole cluster of things at Mars at the top. There's a whole bunch of things in the moon or in Sun, Earth-Moon Lagrange points at L1 pointing towards the Sun, and L2 where Gaia is and where James Webb Space Telescope will go on the other side of the Earth from the Sun. And then you see a few other things like the Solar Orbiter and the Parker Probe that are in the inner solar system studying the Sun, and Bepi Colombo, which is spiraling its way in to get to Mercury. But what I'm going to talk about today in terms of the active missions are the two that are currently visiting asteroids or on the way back from asteroids, which are OSIRIS-REx, the NASA mission to Bennu, and Hayabusa 2, the Japanese mission to Ryugu. And these are two active asteroid missions that we have at the moment. You see they're both in near Earth's orbit. They are visiting near Earth objects rather than asteroids in the main asteroid belt, which is the sort of pink dots around outside of Mars here. And these are obviously a bit more accessible in terms of getting spacecraft there. But before I go into the spacecraft in any detail, I thought I'd just have a little recap on why it is that comets and asteroids are particularly interesting, and of all of these missions all over the solar system looking at various things, why I find the comet and asteroid ones most interesting. And this is because the comets and asteroids are the leftover bits from the formation of our solar system. I quite like this artist's impression of the disk of planets forming around the young sun, because it shows some of the important features. It shows that you've got this kind of lanes of dust and gas that have been carved out by planets forming. It shows that you've got small bodies and comets that are feeling the effects of the sun. But it also, the artist has depicted this with this kind of orange glow in the inner disk and a more kind of cool bluer color further out. And that really reflects how we think the system formed and why we have rocky planets in the inner solar system and gas giants and comets and things further out, because in the hot part near to the sun as it formed, you form rocky things where it's relative, where ice can't condense, and in the outer part you form icy bodies, and then there's more gas around to form the gas giants. And so comets and asteroids are left over from this period, comets from the outer part, asteroids from the inner part. But as we study more and more, we discover there's more and more a kind of a continuum between these. And some asteroids are going to have ices buried within them, and some things that are coming even from further out in the comet cloud have actually got quite a lot of rocky material there. So there's actually quite a lot of mixing going on, and studying these in more detail gives us better clues to understand this process and how planets formed and what our disk was like, where we came from. Then, of course, there's one other reason why we're quite interested in asteroids and comets today, is that occasionally these things do still bump into the Earth. Earth is technically still accreting bits from the disk, just at a very slow rate these days. And this sort of thing does happen, thankfully very rarely. And so there is an interest in what we call planetary defense these days, in actually studying asteroids in case we ever do spot one that's coming our way, to be able to do something about it. Given the way that 2020 is going, probably we should be doing this quite quickly, but we don't know of one coming yet. Okay, so what are we doing with asteroid missions at the moment? We have two things that are flying, OSIRIS-REx and Hayabusa 2. Both of these are what we call sample return missions. So they are going to an asteroid, they are collecting a bit of the surface material and returning it to Earth. And that's what we often call sort of holy grail in planetary missions, is actually going and getting part of it and bringing it back, because the techniques we could apply in Earth-based laboratories are always going to be so much more advanced than we can do with a spacecraft. And we have amazing technology now of kind of miniaturizing mass spectrometers and so on, and the toolkit that we had, for example, on the Philae lander from Rosetta that landed on a comet was an amazing set of equipment. But still, what you can fit into a shoebox and land on a comet, you can always do orders of magnitude better if you can use a laboratory on Earth, if you can use something like Diamond Light Source with this major facility down in Harwell in Oxfordshire, or something like that. There's no way you could build a facility of that size and send it into space. So bringing material back and then being able to use absolutely microscopic fraction of that and samples and turning all of the analytic laboratory facilities we have on it gives you a really detailed information. And so both these missions happen to be going on about the same time. The Hayabusa 2, as its name implies, is the second attempt that the Japanese Space Agency have had of doing this. They previously had Hayabusa 1, which did manage, despite lots of problems, to return a microscopic amount of material, and even from that there were major results. But the second one, where they learned from the first one and fixed lots of things, is now on its way home, having successfully collected a whole bunch of material. So that's going to be great. And then OSIRIS-REx is a NASA version, which is currently in orbit and mapping and looking for its landing site and practicing, and is expected to do a touchdown and sampling later this year. It's also quite interesting that there's some similarity between these objects. So these are the two targets, Ryugu on the left and Bennu on the right. Ryugu is slightly larger, about 1 kilometer across, but both of them have what we call this sort of spinning top shape. they have this sort of odd diamond shape with a kind of pronounced ridge around their equator. And this is actually something which is predicted from an effect called the Oort effect, where sunlight can spin up asteroids. And this is a very slow process, as you would imagine, but just the momentum of photons from the sun landing on the surface, being absorbed, and then being re-emitted as thermal photons at some time later. It gives you an asymmetric force, and that gives you an acceleration. And over a very long period in time, you can spin up your asteroid. And so we think that a lot of shapes like this are caused by the fact that these asteroids at some point were spinning quite fast, and then material slides down to form this ridge around the equator. And in many objects, we think this is also how they formed a moon, because some of the material has been spun off the equator and gone into orbit and formed a little moon around it. And so we think these sort of shapes are actually quite common, particularly in the near-Earth asteroids, which are relatively close to the sun, so they feel this effect more strongly. And so, yes, trying to get samples from these and explore this effect more is telling us a lot about how asteroids form and evolve. Okay, so I'll tell you a bit more details about Hayabusa 2 in particular. Sirius-REx does similar things, but Hayabusa 2 is a little bit ahead of them and does far more cool tricks up its sleeve, so I'll tell you more about this one. So this is a nice little animation, which hopefully is working okay over the internet, which is of what Hayabusa does. I will just play it again. So this is Hayabusa. You see it's got this sort of little mosquito sampling horn, and the whole spacecraft comes and very slowly touches down, and the sampling mechanism shoots some gas into the regolith of the surface, and this shoots the material up the little horn and into the sampling canister. And you also notice there's got a little ball on the ground there. This is the target marker. So the way it does this is it drops these little markers from orbit and then uses that as a visual navigation tool to come down. And Hayabusa 2 is actually packed full of lots of little deployable things. It's basically a whole, aircraft carrier of little toys. It has these little target markers, which are the things in the lower right. It has a selection of different rover type things. So on the left and the right, these Minerva, different size rovers. I mean, these are little round things that are basically the size of, a sort of biscuit tin. And then it also has the re-entry capsule, of course, at the top, which is the one that it still has, because that's where the sample is packed into. And that's the bit that's designed to re-enter Earth's atmosphere and be collected so that we can get stuff to the lab. And then in the top right, there's a mascot lander, which is actually a European contribution. This is a German and French shoebox-sized lander that has a few cameras and experiments on it that was also dropped onto the surface. And then the last thing, which is particularly fun and completely crazy, and there's no way the Europeans would let us try this, but Japanese Space Agency has more of a experimental attitude and will try stuff, is that they have this thing called the Small Carry-On Impactor, which is at the bottom. This is essentially a little bomb that they released from the spacecraft, and the little bomb floats around in space, and then they move the main spacecraft around to the other side of the asteroid for safety, fire the bomb, it shoots a copper projectile into the asteroid surface at very high speed and makes a little crater. Just to do an experiment, just make our own crater, because then you can see, okay, the material inside is fresh. But of course, they realized that then you wouldn't see the actual cratering experiment because you would hide the main spacecraft out of the way. And so then they also had the thing at the top, which is a little deployable camera, which was its own little camera that would float around in space and take images of the explosion and the impact in a disposable way. So the main spacecraft wasn't damaged. So you have this entire fleet of little spacecraft, some of which are, would fit in your hand, all doing this, all investigating this asteroid. And these are some of the nice results from it. So in the top left, this is actual video of the touchdown of it going and sampling. And you can see the surface is not nearly as kind of smooth and sandy as they were kind of hoping for. It's actually got quite some decent sized rocks, but they still managed to get a sample from this going in. You can see as it touches down, it disturbs a lot of the dirt on the surface and the low gravity environment, and this also is floating up away with the spacecraft as it retreats. in the middle, this is a color image from the European lander. So this is what the surface looks like in sort of close up. If you were sitting on the surface, you get this kind of reddish gray, odd looking sort of slightly consolidated material. And then the last little GIF in the bottom there is before and after images of the mini crater that they made with the little bomb. And so they managed to, yes, make a little crater, expose some of the fresh material from underneath. And then in a ridiculously daring piece of flying, they actually then did a third touchdown with the sampling horn inside this new crater, and now have a sample of the interior of this asteroid, which is, yes, spectacularly risky maneuver to do. If you imagine you've already got you've successfully managed to touch down once and then twice to get samples, and you've got this precious sample on board your spacecraft, you then do a third risky maneuver. But they pulled it off, and they've got 3 samples and they're on the way home. We expect that the Americans instead they have the capability to do more than 1 sampling, but we expect they will be more NASA-like and conservative, that if the first one works, they will say, good, we've got it, and come home and not risk it. So. Okay, these are the 2 currently flying missions. The next thing I want to tell you a bit about was we have some planned missions coming up. And so the first pair of missions that I'll tell you about are asteroid missions. These are actually about this idea of planetary defense. This is about trying to deflect an asteroid, a practice run in case we ever decide we see one coming towards the Earth and we want to do this. And so there's a very cunning plan for this, which is what the DART mission, which is the NASA part of this, which is the actual impactor, and then the European part is HERA, which will then go and study the results. As we tend to joke about this, we let the Americans go and shoot stuff because that's what they like to do and they're good at, and then the Europeans are going to go and send the science and study the results and see what happened. But the cunning plan is that what we're going to a binary asteroid system. So this is the Didymos system. The moon going around it, nicknamed Didymoon, it now has an official name of Dimorphos. And the idea is that by impacting the moon of the binary, we can change its orbit around Didymos by a noticeable amount. And the current orbital period of the moon is about 12 hours. And the collision is expected to change that by 12 minutes or so. And that's a measurable amount just by doing telescopic observations from Earth. You can actually, even with a relatively small telescope at the time we do this, because it also has when the impact happens, this near-Earth asteroid will happen to be relatively close to Earth. I think about 11 million kilometers away, but in space terms, in our backyard. And so Didymos will be quite bright, and even with a small telescope, you'll be able to measure a light curve and over 12 hours see when you get some little eclipses because of the moon going around it, and we can measure the period of the orbit of just by looking at these eclipses. So it's a very neat experiment that allows us to really measure how effective slamming a spacecraft into an asteroid is changing its trajectory. And so that is planned to launch next year, and with an impact in 2022. And then the HERA mission will go and study the aftermath some years later. So this is what DART spacecraft looks like. At the top is a sort of CAD drawing of the thing. It has these roll-up solar panels. This is the white tube on the sides. It has these deployable rolling solar panels, which are quite a neat thing. And then in the bottom, it's currently under construction. So this is it at the Johns Hopkins lab in the US and at APL, where they are currently building the thing. And their labs are open despite COVID, and working in a clean room is probably as good a place as any to work because you have to wear a mask anyway. But this thing is still on schedule for being launched next year in 2021, and October 2022 is when it will slam into an asteroid. It also has a sort of ride-along CubeSat provided by the Italian Space Agency, which is officially called Licia Cube, which has some cameras, but is unofficially known as the selfie sat, because of course the main spacecraft will be destroyed when crashing into an asteroid, and so to have any images of close-up images of the impact, it deploys a little small sat to see the effects in a similar way to the Hayabusa 2 did with its little carry-on camera. And then Hero, which is a sort of full-sized European Space Agency mission with a slightly more capable payload, cameras, and its own accompanying CubeSats that are deployed, is expected to launch in 2024, arrive in 2027, and go into orbit around the system and study it in great detail. And so it will be able to measure the properties of the crater caused by the impact and figure out what happened. Okay, the other couple of future missions that are coming from the NASA side are science missions rather than these defense missions. I don't have much on these, but briefly, there's one called Psyche, which is visiting asteroid Psyche, which is an interesting asteroid. It's one of the larger ones in the asteroid belt, sort of 100-kilometer scale things. But it has the spectrum that people interpret as being very metallic. So as if it was, you know, as if you've seen the metallic meteorites where you get this great big lump of iron. Part of the idea is that this thing, it used to be the core of some planetesimal, some larger body that was then destroyed in a catastrophic collision between asteroids. But what you are left with is this iron core. And so that is a fascinating possibility. And that's the idea of this mission, is to go and have a look at what the core of a small planet would look like. And so this artist's impression is all, you know, is sort of trying to give the idea of this great big lump of iron with sort of interesting frozen craters and things on it that the mission will get to. That launches in 2022 and will arrive a few years later. So this is out in the main asteroid belt. And then the other mission that NASA is working on at the moment for small bodies is Lucy. And this actually goes out to the Trojan asteroids, which are this population that is in the same orbit as Jupiter, so relatively far from the sun outside of the asteroid belt, but are 60 degrees ahead or behind of Jupiter in its orbit, in this dynamically sort of stable location where gravitational forces from Jupiter and the sun balance. And there's these clouds of asteroids out there, which we've never visited with a spacecraft, and are potentially very interesting because these could well be more icy objects from the outer solar system that have been trapped in these locations for a very long period over the age of the solar system. So a way to go and see something quite primitive, maybe more akin to a Kuiper belt object, but without having to go to the very edge of the solar system. And they have a very clever and complicated trajectory, which is illustrated at the bottom. Essentially, this thing loops, it does various loops past Earth, and each time picks up some speed and gets a more elongated orbit, and then essentially does this trick of looping all the way out through the Trojan cloud, flying by lots of things, back to Earth, looping around and going out the other side and going and seeing the other cloud. And it has a few other flybys of some main belt asteroids on the way. And that is due to launch next year. So that is well underway as well. Okay, and then the final asteroid mission that I wanted to tell you about is one which there's not an awful lot of information available, which is the first Chinese interplanetary mission. And so they are proposing to do a mission which goes first as a sample return mission to a small asteroid, I mean a very small one, a few meters in size only, which is called 2016 HO3. And this is sort of described as a mini moon or a quasi-satellite of Earth. So it's orbiting around the sun on this yellow ellipse, but its orbit is also 1 year at the same distance as Earth's, and so it's basically always reasonably close to Earth. And as seen from Earth, its orbit appears to go around the sort of the set of circles or ellipses around Earth on the left there. So it's this kind of interesting thing that's not technically orbiting around the Earth, but it stays with the Earth. And so it's discovered a few years ago in 2016, as its name implies, and quite an interesting little target for a sample return to go and have a look at. It'll be by far the smallest asteroid that we've ever visited with a spacecraft. And so it'll be quite interesting to sort of see what that looks like. It may well be just, you know, a single lump of rock. But anyway, that then grabs a sample of that, comes back to Earth. And then the reason why I'm quite interested in this mission, and I have a small involvement in it, is that after the main spacecraft has dropped a sample return capsule at Earth, it will swing around Earth, take a swing around Mars, and head out into the main asteroid belt and visit an object called El Spazaro, which is something we call main belt comet. Now, these are these recently discovered, only in the last couple of decades, population of comets that are orbiting within the asteroid belt. These are some of these objects that kind of are blurring the boundaries between asteroids and comets. They have an orbit which is entirely asteroidal, more or less circular, within the main asteroid belt. So in the warmer inner solar system part where we don't expect there to be ice, and yet the image on the bottom, it shows it has a faint tail every time it comes close to the perihelion part of its orbit. So it has cometary behavior. And so this is an object which is fascinating. I led a mission proposal to ESA a few years ago to go and send a mission there, which wasn't selected in the end, but it's definitely a fascinating population to visit. And so, yes, at the moment, it appears that this is the plan for the Chinese mission to go there. But this is all still kind of in development, sort of decided, not quite clear what's happening with it. And I say that as someone who's nominally involved. So we will find out more as that goes along. Anyway, main belt comets brings me to comet missions. And really, I'm more of a comet guy than an asteroid guy because they're far more interesting. They do stuff, they have activity. And so I'm going to go on to missions to comets, or one in particular. These are all the comets we've visited by spacecraft before, starting with Halley in the 80s. And you can see Halley is quite a bit bigger than the other comets that we visited in between. But until we had the Rosetta mission with 67P in the middle there, all of these missions were just fast flybys. And so all you got was a handful of images like this in a very short period of time. And these taught us an awful lot. But then Rosetta gave us this order of magnitude step forward by orbiting a comet, by sending a lander down, studying it in great detail. But now that Rosetta is done and has been for a few years now, or at least in terms of operations, we're still working on all the data. We're now planning for the next cometary mission. And the next cometary mission returns to a flyby mission because it's a much smaller class of mission than Rosetta was, with a smaller budget. But it is still going to do something quite new. And so this is a mission that's called Comet Interceptor. And this one I know a bit more about because I'm one of the leaders of this mission. And so the rest of this talk, I'll tell you a few more details on Comet Interceptor. Now, the point of Comet Interceptor is to go to a dynamically new comet, a comet that is coming out of the Oort cloud for its first approach to the inner solar system. So the first time that this thing has felt the heat of the sun, potentially since it was formed, something very pristine. Because what all of the previous comets that I showed you on the last slide have in common, even Halley that has, a 70-odd year orbit, is these things have been past the sun many times. Their surfaces have evolved. They've got, one of the things we found with Rosetta is that there's a very substantial amount of the dust that is carried off, doesn't go into the coma and into the tails, it actually falls back down. Slowly in a low gravity environment, but it does rain back down and covers other areas of the surface. And so what we see on the surface of a comet, even though these are some of the most pristine objects we can study, is that they're still quite evolved if we go to one that's that we know well because it's orbiting the sun many times. So the idea of Comet Interceptor is to go to a brand new comet that's coming in for the first time, and will be less processed. And so this is a kind of sketch of this idea. that on the top is the sort of slow route from the Kuiper belt, or where we've seen from New Horizons, the first objects there, through the sort of Centaur region, which is the area of space where the giant planets are, and small bodies are orbiting in that region are called centaurs. We've yet to visit any of those. But that takes, you know, tens of thousands of years to kind of slowly for orbits to evolve through that period. And then eventually they then evolve inside of the planets and become comets when they're into the inner solar system. And they have this activity as they come close to the sun, and they evolve. And so we have the Jupiter family comets, which come from the Kuiper belt. We have long period comets and things like Halley that have come from the Oort cloud originally, but are now on relatively short orbits. The idea is to study something dynamically new, or at least a long period coming from the Oort cloud that we haven't discovered before, because these things come all the way in and out in a matter of years and don't have the thousands of years to slowly evolve. So you see a really pristine thing. Now, that raises some challenges, because of course trying to send a spacecraft to something that you haven't discovered yet is challenging for engineering team. So the only way you can hope to go to something that's dynamically new is to have the spacecraft already designed, built, ready and waiting for a kind of generic target, and then go to the target once you find something coming. And then even that would take at least a few years to kind of react and respond and get ready. But that is something that we can start planning for in the next few years. So the plot at the bottom is showing the discovery distance from Earth of comets over the last couple of hundred years. And you'll see that for most of this time, because these were discovered visually, comets were already within a few astronomical units of Earth and already in the inner solar system when they were picked up. And so you would maybe have a few months to study a comet before it disappeared again. But now with the more advanced surveys, things like pan-stars and so on, we're already discovering occasional comets at quite large distances from the sun, many years in advance of their perihelion. And with LSST, which is, well, it has the old name on here, it's now the Vera C. Rubin Observatory's Legacy Survey of Space and Time, which is an impressive backronym just to stop us having to change all the documentation that says LSST. The LSST is this 8-meter survey telescope being built in Chile that will scan the entire sky every few nights down to a depth of 24th magnitude. And it will be a phenomenal discovery machine for solar system objects, for transients, for all sorts of things. And we expect to find comets with this system with 5 years warning or so. That's still not time to plan and build a spacecraft. Even Comet Interceptor, which is the first fast class mission for ESA, is 10 years or so between proposal and launch. But it gives us enough time to react if we have the spacecraft ready. And so the way that we do this is actually we design, we build, and we even launch the spacecraft before we potentially know what the target is. And the target and the spacecraft then has to wait in space, and we have a parking orbit until we find a comet that is going to pass through a region we can reach. And then we have a reasonably rapid reaction, months to years, to go and intercept it. And this is sort of a little sketch of how this works. We launch to actually one of these Lagrange points that I mentioned at the start of the talk, the L2 point. The reason we go there is that we're actually hitching a ride with a space telescope, the Ariel telescope, which will study extrasolar planets. And that has a bit of spare mass on its launcher. And when it launches in 2028, we go with it and we go to this L2 point, which is a stable place where the gravitational forces between Earth and the sun balance in a certain way, and with relatively little fuel, you can park there for a long time. And that's one of the reasons why things like Ariel and JWST and Gaia and various space telescopes go there, but it's also a good place for us to park and wait for a comet. And so while we're waiting, LSST and others will be scanning the skies, and we'll eventually find some comet at a large distance that we like the look of. we're able to compute its orbit, figure out where it's going, and find a place in space where it's crossing the ecliptic plane that we can reach, calculate where that's going to be, and then we fire the rockets and we head off towards it to make an interception. And we meet this comet as it crosses the orbital plane of Earth, and have a fast flyby encounter with it. Now, this is a fun idea, and then we had to convince ourselves, and more importantly convince ESA, that this could potentially have worked. And so what we did was we looked at an example. So here is Comet NEET, 2001. This was a dynamically new comet that was a reasonably bright one and therefore well studied. And then so you have nice images of it, but also, I mean, we could pick this one and say, well, this is where it was discovered and what its orbit was like. It was actually discovered by the NEET, Near Earth Asteroid Tracking Survey, and NEET had a 1 meter class telescope. And so if we scale up just on LSST being much more powerful, when would LSST have discovered the same comet? It would have found it potentially in 96. Here we imagine that the mission launched sharing a ride with the XMM telescope, which launched in 99. It didn't go to L2, but we just had to pick a date, so that seemed like as good a date as any. You can see we'd have waited around for a couple of years at the L2 point, and then we'd have had the encounter in 2004. And we couldn't have done it in the past because NEET actually discovered this comet a month or so after we'd have had to leave to intercept it. But LSST really enables this because we would have discovered it years in advance, actually before we even launched into our parking orbit in this case. And this is what the orbits would have looked like. You can see that the spacecraft doesn't actually ever get that far away from Earth. It just meets the comet when the comet is passing Earth's orbit. But we spot the comet a long way out and are able to make a prediction. Okay, what do we do when we get there? Well, one of the other neat things with the Comet Interceptor, and the other thing which is quite new, is it's actually made up of 3 spacecraft. It has a main spacecraft, which is provided by ESA, which will have a flyby at a relatively large distance, about 1,000 kilometers. This is still well within the cometary coma, but it's outside of the most dense region in the center, where the chance of impact with some dust grains at very high velocity is lower. It is the main spacecraft. It has the propulsion and communication system, and then it has its own science payload that will study the comet from reasonably large distance. And then it also takes along 2 smaller probes that are released and sent towards the comet. And the idea with these is these can take a lot higher risk and go into the inner coma and to the dangerous region. And if they don't come out the other side, that doesn't matter because they're streaming their data in real time, and we get all of the images and the other measurements to as close as we possibly can. And then it means you can do this sort of high risk, high gain approach, which is a very novel way to do spacecraft. Spacecraft engineers tend to not like taking any sort of risk at all. And so designing in risky elements is quite good fun. But yeah, these 2 small spacecraft, one is provided by JAXA, so it's based on a lot of the technology that's going into High Vista 2 at the moment, and the other is also provided by European Space Agency, and that's the one that gets the closest. We have a little sort of sketch animation of these things that they fly through. The A is the main spacecraft that has a slightly further flyby. B1 and B2 get closer. From A, we actually have the main camera of the main scientific camera is actually on A, even though it's furthest away. It's big enough that we can put a real kind of telescope on there, and it will get both images of the whole thing, but also the higher resolution images at closest approach. But then we also have a camera on the other spacecraft, which will see a slightly different view as it goes past. And by combining these, we can actually get a kind of 3D snapshot of the comet, which is a nice thing to do because, as I said, all previous flyby missions, you just get a handful of images at one geometry, and so trying to reconstruct it afterwards is a challenge. So this is the Comet interceptor plan, and yeah, each of these spacecraft has a combination of remote sensing cameras, spectrographs, and in situ measurements. And it's currently being developed, and we're working on all the details of this thing. But it will launch in 2028, maybe a few years waiting in space, and then at some point in the 2030s, we encounter a dynamically new comet or something coming from the Oort cloud. And then the last slide that I have on this, because it's nearly always a question, is that people say, well, if we can encounter an Oort cloud comet, can we encounter an interstellar comet? Because we had Oumuamua a few years ago, and we now have Comet Borisov last year and this year. That the idea of that we might detect something coming from another star system and be able to get spacecraft to it is obviously very exciting. And so it is possible that we can do this. There's nothing technically that will be different meeting an interstellar comet than meeting an Oort cloud comet. It's just very unlikely that we have one in the right place at the right time. There was a study on this by some guys in the US that looked at this, and they thought that on some very, when we'd only discovered Oumuamua and trying to do all of our statistics with n=1, that maybe LSST would find one of these objects per year, and over 10 years it might find one that would come close enough and that we'd have enough warning to get spacecraft to. But their model was to assume spacecraft sitting waiting in a hangar at the Cape, and a dedicated Falcon Heavy launch, so it had a lot more fuel and a lot more possibility to get there. A lot higher delta V is the term, and so this is not something we can do with Comet Interceptor because it's a much smaller class of mission. We don't have our own dedicated rocket. But if we were very lucky, we would definitely like to encounter an interstellar object, but we'd have to be very lucky. Okay, so I'll wrap up just by giving a little summary, which is that hopefully this has been an interesting quick tour of what's going on with asteroid and comet missions at the moment. We're in an exciting time, and we're just finishing this period with the Rosetta mission, which was many years of detailed exploration of a comet, and we'll still have many years more analyzing that data. And of course, New Horizons flying through the Kuiper Belt and seeing the very edge of our solar system. But the sample return missions are potentially very exciting in terms of getting detailed information from laboratory studies. And then also this idea of doing a planetary defense experiment, doing something where we actually try and change an asteroid and move its orbit, is a really neat idea, and that's coming up very soon. So it's launching next year with a collision in 2022, and then slightly longer timescale, but keeping me much busier at the moment is Comet Interceptor, which we're now working on the details of. And if you want to know more about that, we also have our website, and you can follow the mission on Twitter on Comet Intercept as well. And with that, I'll stop and take any questions you might have. Thanks very much.
Thank you, Colin, for a fascinating presentation, and thank you very much for jumping in at the very short notice as well.
No problem.
I'm pleased to say that I do now have a copy of Sandra's presentation, so I'm confident that will be going ahead at 2:30. For anyone who wants to ask questions, there's for most of your screens on Zoom, you'll find a Q&A button at the bottom of the screen. For a few different sort of types of hardware, you might find the Q&A button in a different place. And I'll try to keep an eye open for anything coming in on YouTube to let you know. Oh, I do see a comment from James Dawson on YouTube saying, "Excellent talk, Colin, thank you."
Oh, thank you very much.
We have a couple of questions in. The first one was from partway through, and this is, I may have missed it. Sorry, this is from Pete Sherman of Sigma, and he's saying, I may have missed it, but what does DART stand for?
DART is the double asteroid redirect test, because it goes to this binary system, so it's double asteroid. But this is one of these good astronomical acronyms where you think of the thing that would be good to call it, and then you figure out the acronym afterwards. So, but yes, DART is double asteroid redirect test. So.
And then the next question is from Paul. And firstly, thank you for such an interesting presentation. What is the most significant finding that Comet and Asteroid missions have identified to date, and how has this changed our understanding of the solar system?
Well, thanks. Yeah, so one of the big things I would say was coming out of Rosetta, which was a sort of, you know, the biggest Comet mission we've had in recent times, or ever really. Was that this thing that it revealed a lot about the way that comets evolve and change, and that our ideas of these things being super pristine are not as much as they were, which was part of the inspiration for following up with Comet Interceptor. But it showed a lot of this fallback and this changing surface. But some of the most exciting results from Rosetta also came from the mass spectrometer, from measuring in detail the composition. And so it revealed that the comet has a lot of sort of organic chemistry. It has a lot of carbon-based stuff. It has a lot of the basic ingredients for life, even. You know, up to even sort of simple amino acids, which are the building blocks of proteins. We found these chemicals within the comet. And so while we think now that possibly the water on Earth and the oceans didn't necessarily all come from comet impacts, or at least not all comets like 67P, because of the isotope ratios of water were different on the comet than they are on the Earth, we did find that an awful lot of the other chemicals that you would want for life did exist there. So it gives you an idea that comets impacting the early Earth, I mean, dropping a few of these comets into the ocean on early Earth really gives you a lot of the basic ingredients, and potentially gives you a lot of the head start for life. So that's definitely one of the most interesting results in my mind from Rosetta.
Thank you, Colin. We have a question in from James Dawson on YouTube. You say there are ices in asteroids and stony material in comets, but are there also metals in comets?
So, and small amounts, yes. So one of the things that the Stardust mission found a decade ago, so this collected grains from a cometary coma in sort of an aerogel, like tennis racket sampling mechanism. So this is the only sample return mission we've managed to do for a comet, and so it couldn't match speeds with the comet and land and get from the surface and then bring it back, because that is something that people are talking about for a future mission, but is hugely complicated and difficult to do. But instead it kind of swept through the coma and grabbed some of the grains as it did by letting them impact into this aerogel, this really weird, light, low density material. And that slowed the grains down and captured them. But even the collision, even in this sort of slow capturing mechanism, you lose all of the ices and the organic material. And what you were left with at the end of these grains was actually quite a lot of little metal grains and sort of lumps of metal, of things that must have formed quite close to the sun. So that implied that you really have quite some stirring of material, of, you know, metals that form close to the sun being embedded in comets that form far away. And yeah, now we find evidence for water and other ices in the asteroids relatively close to the sun. So there's definitely a continuum of material mixed around in these small bodies.
Thank you. We're now having a few more questions coming in on Zoom. From Gordon Mackey, excellent talk. What are some of the key things we hope the analysis of the Ryugu rocks will tell us?
So one of the interesting things there is that is to do a comparison between that and the tiny amount that they managed to bring back from Itokawa, which was the first Hibis mission. The first mission, they had all sorts of problems with it. The sort of sampling mechanism didn't work. In the end, they've realized that just by chance, some of the material that was thrown up, like you saw in that video, found its way into the sampling mechanism. And when this thing managed to get home, which was also a challenge because some rocket motors failed and they had to kind of jury rig it and limp back. And it was a really clever piece of space flight to get home at all. They did manage to scrape out some microscopic samples from what looked like a very clean sample container, but that was from a rocky type, S-type asteroid, whereas Ryugu is from a more primitive type, so something that may be more related to Comet originally, of C-type asteroid. And so the comparison of mineralogy of saying, what do these look like? How different are they? Will be one of the key things. And then also will be how much variation do you get within a single sample from a single asteroid? Because actually, if you bring back, you know, a few hundred grams, you will, and you can do these measurements on individual grains, you might find that you've got, as I said, some metals, some rocks, some ices, some whatever, all within the same body. I mean, there won't be ices that make it back through the sample, but there might be evidence that there was ice in the past within the mineralogy. So that would be very interesting.
Next, we have a question from David Boyd. Could the dart impact on Dimorphos could the dart impact on Dimorphos change its orbit such that it would no longer eclipse?
We don't expect that's the case. No, it will change the period of the orbit around by, yeah, they think about 12 minutes in 12 hours. But to change the plane of it would be very difficult. The idea is to hit it pretty much head on, and so you get the maximum change in the speed around the orbit, and so we get the maximum measurable change. But changing the plane of it would have to be a very significant amount for it to no longer eclipse, and that doesn't seem to be possible. So.
Next, a question from David Knight. Thank you. How much material is expected to be returned from Hayabusa 2?
It's of order sort of tens to hundreds of grams or so. So it's not, you know, boulders and kilograms of it, but it's measured in grams. I think a few tens of grams, if I remember rightly. But yeah, if you compare with the, you know, 20 odd major science results they managed to get out of microscopic sample from the Hayabusa 1, it's already a huge amount. And then there's a very complicated plan for how to carefully store it and carefully, you know, make use of very small amounts of this in the most efficient way possible. So it becomes a very, very precious material, but you can do an awful lot with a very small sample of it.
Thank you. Next question we have is from someone who's joined Zoom anonymously, which is, will any of this settle the question of the origin of Phobos and Deimos, giant collision or captured asteroids?
I mean, I guess that there's also there. I mean, I didn't talk about them because I guess they can fit into this category because it's small body missions. If you think of them as captured asteroids, there are plans for missions to go to Phobos and Deimos as well. And so actually, I guess those, when you compare the results that those missions might get with the asteroid missions, is then you can say, okay, do these things look like asteroids or do these things look like a bit of Mars? So yes, it can help answer that, but in comparison with results when the mission goes to one of those.
Thank you, Colin. And the final question for the moment is again from James Dawson on YouTube, and that is, how big are the biggest things in the Oort cloud?
That's an excellent question. Nobody knows. I mean, you could have a planet-sized thing out there and we wouldn't know. I mean, you could have a big planet, a Jupiter-sized thing out there, and it would be too faint for us to see. So there's all this discussion on this, you know, another planet in the, not even as far as the Oort cloud, maybe inner, depends what you call the boundaries, but inner Oort cloud, maybe a few hundred astronomical units out rather than tens of thousands, which is where you go out to in the Oort cloud. There's also discussion that there's another planet-sized thing at the edge of our solar system, and there's some evidence for it, but that's very much debated. And there's a big, you know, there's a lot of ongoing interest in this search at the moment for, is there another planetary-sized thing at the edge of our solar system? It's perfectly possible that there's a planetary-sized thing out in the Oort cloud, and we wouldn't know because it's just so far away that it wouldn't reflect enough light for us to pick up with current telescopes.
That appears to be all the questions. So may I thank you once again, Colin, for coming in at short notice and also giving such a fascinating and informative talk on all of the spacecrafts, missions which are going on around the solar system. But thank you very much. And for anyone who didn't capture all of this, the video is on YouTube. I'll do some editing later today to cut out the 15 minutes or so where we were having the initial problems to make it easier to watch. Thanks again.
Thanks very much. Bye.
Thanks everybody, much appreciated.